You begin by looking up, not with effort, but with permission. The night sky is already there, waiting above you like a calm ocean turned upside down. You do not need to understand it yet. You only need to rest your attention upon it. The stars appear steady, pinned gently into darkness, quiet and unchanged. But this stillness is only a first impression, like a sleeping face that hides a dreaming mind. As you breathe slowly, you notice how natural it feels to assume that distant lights remain fixed. Your senses prefer stability. Your thoughts like unmoving anchors. Yet the universe is not built from stillness. It is built from motion layered upon motion, like soft rhythms nested inside larger rhythms. Even now, without feeling it, you are traveling. Your body rides a rotating planet. The planet circles a star. The star moves through a galaxy. The galaxy drifts among others. Motion is not the exception. Motion is the background truth. But distance makes movement look like silence. Imagine sitting beside a faraway mountain. From miles away it seems frozen and permanent. But if you could watch it for 1,000,000 years, you would see it breathe, rising, folding, eroding, reshaping. Time changes what distance hides. Space does the same to motion. The stars seem still because they are so far away that their movements unfold slowly across human lifetimes. Their journeys are measured not in hours, but in ages. What looks fixed is often simply patient. You let that thought settle gently. Some of those stars, perhaps many, are not alone. Around them move unseen companions. Worlds with stone and wind. Worlds with oceans or clouds of gas. Worlds of ice, worlds of fire, worlds stranger than any landscape you have known. These planets do not shine by their own light. They travel quietly, reflecting only a faint whisper of their star's glow. That is why they remained hidden for so long. If you place a candle beside a lighthouse, the candle disappears in the glare. Planets near stars face the same problem. Their stars outshine them so completely that direct sight becomes nearly impossible across interstellar distances. So astronomers learn not to look for the planet itself, but for the effect it leaves behind, like footprints instead of feet. You begin to sense a theme forming. In astronomy, presence is often revealed by influence. A planet can reveal itself by pulling slightly on its star. Not enough to drag it away, only enough to make it sway. Two dancers do not circle with one standing perfectly still. They both move around a shared center. The heavier dancer moves less, but never not at all. Stars, too, perform this gentle sway. If you watched a star closely enough, with sensitive instruments and long patience, you would see it shift forward and back in a tiny repeating pattern. A quiet wobble. A gravitational nod. This motion is the signature of an orbiting world. The planet remains unseen, but its pull is measurable, like hearing a partner's step through a closed door. You rest with that image, the invisible made known through relationship. There is another method too, softer still. Sometimes a planet passes directly between you and its star. When this happens, the star's brightness dims ever so slightly, a fractional dip, like a moth crossing a lantern. The change is small, often less than 1%, but it is regular. Predictable. Rhythmic. Light becomes a clock. You imagine watching that steady glow night after night. Then a tiny fade. Then brightness restored. Then, after a fixed interval, the same dimming again. A pattern emerges. A hidden orbit announces itself not with a shout, but with a blink. This is how thousands of distant worlds are discovered. Not by seeing them, but by noticing when they briefly interrupt starlight. Discovery, here, is an act of listening with eyes. You realize something comforting: the universe does not hide itself out of secrecy, but out of scale. Its signals are subtle because its distances are vast. With the right patience, even faint messages become clear. Patience becomes a scientific instrument. You picture astronomers as caretakers of long measurements. They build devices that do not grow bored. Telescopes that stare without blinking. Sensors that count photons like falling grains of sand. Where human attention would drift, these tools remain faithful. They collect the quiet evidence of motion. And motion is the key to tonight's doorway. Brightness can deceive. A star may shine steadily whether it hosts planets or not. But motion cannot easily lie. Motion carries structure. Motion implies cause. When something moves in a repeating way, there is usually a partner nearby, shaping the path. You return to your breathing and notice your own rhythms: inhale, exhale, rise, fall. Your chest reveals your breath through motion. A still chest would hide it. Movement is message. So it is with worlds. You imagine yourself far from Earth, watching our sun from a distant vantage. You would not see Earth directly. It would be too small, too dim beside the solar blaze. But you could detect a tiny dimming once each year as Earth crosses the sun's face. You could measure a slight solar wobble caused by Earth's gravitational tug. From these two motions, the dip and the sway, you could infer an entire planet with oceans and weather and quiet night skies of its own. All from motion. The thought feels intimate. Your whole world detectable as a pattern in light. You let the feeling soften you rather than shrink you. To be measurable is not to be small. It is to be connected. The universe reads relationships more easily than objects. Interaction speaks louder than isolation. Above you, the stars continue their slow choreography. None are truly fixed. Each participates in layered orbits: planets around stars, stars around galactic centers. The cosmos is less like a painting and more like a dance performed at a tempo so slow that only careful watchers notice the steps. Tonight, you become one of those watchers. Not with instruments, but with imagination guided by truth. You understand now that when you look up, you are not seeing still lights but paused stories. Every point may host circling companions. Every steady glow may conceal a family of moving worlds. Stillness, you realize, is sometimes only motion too gradual for hurried eyes. And as your thoughts drift among these hidden paths and quiet revolutions, you begin to wonder what invisible force teaches all these bodies how to move together without collision, without confusion, what gentle rule shapes every orbit you cannot yet see. You drift now from the quiet discovery of motion into the quiet cause behind it. Movement in space is not random wandering. It is guided, shaped, and gently persuaded by a presence you cannot see and cannot touch. You have felt it since your first moment, though you rarely notice it directly. It holds your feet to the ground and keeps the air close to your skin. It draws raindrops downward and lifts ocean tides toward the moon. This presence is gravity, but tonight you do not meet it as a formula or a rule. You meet it as a relationship. Gravity is not a command. It is a conversation between masses. Imagine two objects in a silent room. They do not speak, yet they lean toward one another. Not from desire, not from intention, but from the shape they give to space itself. Mass is like weight placed on a stretched fabric. The fabric bends, and nearby travelers follow the curve. In this way, gravity is not a hook that pulls, it is a slope that guides. You do not feel the slope because you and the ground curve together. When you lift your hand and let it fall, it is not being grabbed. It is following a path shaped beneath it. Like a marble rolling across a gently dipped surface, it moves where the geometry leads. The earth shapes the path. Your hand follows it. You rest with that image, space not empty, but softly contoured. Now you carry this understanding outward, beyond your room, beyond your sky. A star is heavy beyond easy imagination. Its mass bends the surrounding structure of space deeply. Nearby objects, dust, rock, gas, planets move along those curves. Not because they are captured like prisoners, but because they are guided like boats entering a current. An orbit is not a chain. It is a balance. You picture a planet beside a star. If gravity alone acted, the planet would fall inward. If motion alone acted, the planet would fly away. But both act together. Forward motion and inward curve meet and agree on a path. The result is a continuous fall that keeps missing the center. This endless missing is what you call orbit. Orbit is falling with grace. You can feel this more easily with a simple image. Imagine throwing a stone forward. It falls to the ground. Throw it faster, it travels farther before landing. Throw it fast enough, and the ground curves away beneath it at the same rate it falls. Now it never lands. It circles. It becomes a satellite. You are surrounded by such falling objects. The moon is falling around Earth. Earth is falling around the sun. The sun is falling within the galaxy. Falling, yet never arriving. There is something soothing in that motion without impact, descent without collision. Gravity also explains why orbits are rarely perfect circles. Circles are special cases, delicate balances of speed and distance. Most real motions are slightly uneven, slightly stretched. These stretched circles are called ellipses. You can think of them as circles that have taken a long breath and expanded in one direction. An ellipse has two special points called foci. A star sits at one of them, not at the center. This small offset changes everything. It means a planet is sometimes closer, sometimes farther, always adjusting speed as it travels. Nearer means faster. Farther means slower. The orbit becomes a living rhythm instead of a mechanical loop. Speed becomes a response to distance. You begin to sense that gravity does not demand uniformity. It allows variation. It writes laws, but within them, it permits personality. Each orbit carries history, how the system formed, what disturbances occurred, which neighbors passed close long ago. Nothing moves without memory. Consider two planets passing near each other early in a system's life. Their gravitational conversation briefly grows louder. Paths shift. One orbit stretches. Another tilts. The change may last billions of years, all from a short encounter. Like a brief meeting that alters a lifetime, gravity preserves the echo of close approaches. You breathe slowly and imagine space not as emptiness, but as influence extending invisibly in all directions. Every mass speaks gravity continuously. The larger the mass, the louder the voice. Distance softens the volume but never reduces it to zero. Even you bend space slightly. Your influence is real, just too small to notice without impossible instruments. But scale does not change truth, only detectability. Gravity is universal participation. There is also a tenderness to its fairness. Gravity treats all mass the same way. A stone and a feather fall with equal acceleration when air does not interfere. Differences you see on Earth come mostly from resistance, not gravity itself. Remove the air, and inequality disappears. The universe, at its deepest mechanical level, is strangely impartial. This impartiality allows prediction, and prediction allows discovery. When astronomers observe a star's gentle wobble, they are watching gravity's conversation made visible through motion. The star is not misbehaving. It is responding honestly to a partner. Measure the wobble carefully, and you can estimate the unseen planet's mass and orbit. Gravity becomes a translator between hidden worlds and patient observers. You realize now that gravity is not only what holds systems together, it is what reveals them. Without gravity, planets would not orbit, stars would not form, galaxies would not gather. But also, without gravity, nothing could be detected indirectly. No wobble. No transit timing shifts. No orbital resonances. The same force that hides planets beside bright stars also provides the methods to find them. A concealment paired with a clue. You let that paradox feel comforting rather than confusing. Nature often works this way, offering a lock and the key in the same design. As systems grow more complex, gravity writes more intricate music. Multiple planets create overlapping pulls. Their orbits adjust into stable patterns or unstable ones. Some fall into resonances, repeating timing ratios like musical intervals. 3 orbits for one planet match 2 for another. The pattern repeats like a lullaby beat across centuries. Cosmic rhythm emerges from simple attraction. And yet, small changes matter. A slight increase in mass. A minor shift in distance. A passing star long ago. These can reshape the architecture of an entire system. Gravity is gentle moment by moment, but powerful across time. Like water shaping stone, persistence becomes transformation. You feel the scale of that patience and let your thoughts slow to match it. Nothing in orbital motion is hurried. Even the fastest close-in planets move with steady commitment, not urgency. They are not racing, they are following curves. The curves are the message. And as you settle into this understanding that motion follows shape, that shape comes from mass, that gravity is the quiet sculptor of every path, a new curiosity begins to form. If gravity guides all motion, and motion reveals hidden worlds, then perhaps the smallest changes in light and timing are enough to map planets you will never see directly. And you begin to wonder how a flicker of starlight can become a map of an unseen orbit. You settle now into a softer kind of seeing. Not the seeing of sharp edges and bright shapes, but the seeing of changes, small, repeatable, meaningful changes. The kind you might miss if you hurry. The kind that only reveals itself when you stay. Most worlds beyond your solar system are invisible to even the most powerful telescopes. They are too small, too dim, and too close to the overwhelming glare of their stars. Trying to photograph one directly is like trying to spot a drifting snowflake beside a stadium floodlight from miles away. So astronomers learn a gentler skill. They stop trying to see the planet itself. Instead, they watch what the planet does. You can understand this easily. You may not see the wind, but you see leaves move. You may not see a heartbeat, but you see a pulse in the wrist. Presence is often revealed through effect. Cause introduces itself through consequence. A distant planet is known the same way. You imagine yourself watching a single star for a very long time. Not glancing, watching. Measuring its light with instruments sensitive enough to notice changes smaller than a fraction of a percent. To your eyes, the star would look steady. But to a patient sensor, it has texture, variation, a living signal. Stars are not perfectly constant. They shimmer slightly. They ring with internal vibrations. Their surfaces rise and fall with hot gas currents. But these changes are usually irregular, like the sound of wind in trees. A planet passing in front of a star creates a different pattern. It produces a dip that is smooth, shallow, and repeatable. This method is called the transit method, though you can think of it as a scheduled shadow. When a planet crosses the face of its star from your point of view, it blocks a tiny portion of the light. The star dims briefly. Then the brightness returns. After one full orbit, the dimming happens again, nearly identical in depth and duration. Pattern becomes proof. You picture it like a moth crossing a lantern again and again at perfect intervals. If it passes every 10 nights, and always dims the glow by the same small amount, you would begin to trust the rhythm. Random flickers do not keep appointments. Orbits do. From the depth of the dip, astronomers estimate the planet's size. A larger planet blocks more light. From the timing between dips, they measure the length of the planet's year, its orbital period. From the shape of the dip, how quickly the light falls and rises, they learn how centrally the planet crosses the star's disk. A curve of light becomes a ruler and a clock. You rest with how delicate this is. Many detected brightness changes are smaller than 1 part in 10,000. Detecting them requires instruments above Earth's atmosphere, where air does not blur the signal. Space telescopes become quiet listeners, free from weather and daylight, staring without interruption. Patience again reveals what brightness hides. But transits alone do not tell the whole story. A small planet close to its star can produce the same dimming as a larger planet farther away if the geometry differs. Light gives size, but not weight. For mass, astronomers return to motion. You remember the gentle stellar wobble from earlier, the gravitational sway between star and planet. This is measured through something called the radial velocity method. The name sounds technical, but the idea is simple and almost musical. Light carries pitch. When a star moves slightly toward you, its light shifts a tiny bit toward the blue end of the spectrum. When it moves slightly away, it shifts toward red. This is the Doppler effect, the same principle that makes a passing siren change tone as it moves by. Approach raises pitch. Departure lowers it. Stars sing their motion through color. The shift is extraordinarily small, far too subtle for human eyes, but spectrographs can measure it. These instruments spread starlight into detailed rainbows and mark the positions of spectral lines like notes on a staff. When the star moves, the lines slide slightly. Back and forth. Back and forth. A repeating drift. That drift is gravity speaking. From its amplitude, astronomers estimate the planet's mass. A heavier planet pulls harder and makes the star move more. Combine mass from the wobble with size from the transit, and you gain density. Density tells you whether a world is likely rocky like Earth, gaseous like Jupiter, or something in between. Weight and width together suggest composition. You begin to feel how indirect knowledge can still be intimate. You do not see the planet's mountains or clouds, yet you know its bulk, its path, its year length, even hints of its structure. Like knowing a person by their footsteps, their breathing, their timing at the door. There are other listening methods too. Sometimes multiple planets orbit the same star and tug on each other slightly. Their transits occur a little early, then a little late, compared to perfect schedules. These timing variations reveal additional hidden worlds, partners that never cross the star from your viewpoint but still leave fingerprints in the clockwork. Gravity leaves margins notes in the timetable. In rare cases, astronomers capture direct images of exoplanets. But these are usually very large planets far from their stars, seen in infrared light where the contrast is kinder. Even then, the images are soft and few. Most of what you know comes not from pictures, but from patterns. This is a different kind of astronomy than you might expect. Less like photography. More like listening through walls. You feel the calm dignity of that approach. It does not demand spectacle. It honors subtlety. It trusts repetition. It waits for confirmation. One dip is interesting. 3 identical dips are evidence. 10 are discovery. Science here behaves like a careful sleeper, turning slowly, verifying comfort before settling. You imagine rows of data points, brightness measurements plotted across months and years. At first they look like gentle noise. Then a small valley appears. Then another at the same spacing. The pattern strengthens. Confidence grows. A world is added to the catalog. Not seen, but known. Thousands of exoplanets have been found this way. Each one first appearing as a faint curve in light or a slight color shift in a spectrum. Entire planetary systems revealed as repeating signatures. Some with tight, fast orbits. Some with long, cold years. Some arranged in resonant patterns like harmonic chords. All discovered through attention to change. You let this idea soften into something personal. In your own life, too, what matters most is often revealed not in single bright moments, but in steady patterns, habits, rhythms, returns. Presence shows itself through consistency. The universe seems to agree. As your thoughts drift, you realize that every detection method so far depends on alignment and geometry, on how systems are tilted relative to you. Only certain orbits produce transits. Only certain angles produce measurable wobbles. Many worlds remain undetected simply because their paths do not cross your line of sight. Which means the sky is fuller than the catalogs. You rest with that abundance, unseen, moving, real. And as you grow comfortable reading planets through motion and light, another question begins to form gently at the edge of your awareness. If these worlds reveal themselves through their paths, then the shapes of those paths must carry deep meaning, and not all paths are drawn the same way. You begin this chapter by imagining a line that never quite closes, a path drawn not on paper, but in space. When you first picture an orbit, your mind likely draws a circle. Smooth, even, reassuring. A perfect loop around a shining center. Circles feel complete, like lullabies that resolve exactly where they began. And for a long time, humans believed the heavens must move in circles, because circles felt worthy of the sky. But the universe, while elegant, is not obligated to be perfect in that particular way. Most real orbits are not circles. They are ellipses. An ellipse is like a circle that has exhaled and gently stretched. Not broken, just lengthened. If you drew a circle in soft clay and pressed lightly from two sides, you would create something close to an ellipse. Still curved. Still closed. But no longer uniform in distance from the center. Except in an ellipse, there is no single center. Instead, there are two quiet anchor points called foci. You can think of them as balance points, places that help define the curve. In planetary motion, the star sits at one focus, not in the middle. This small shift changes the entire story of the journey. You picture a planet traveling this stretched path. At one part of its orbit, it passes closer to the star. At another part, it travels farther away. Distance breathes in and out across the year. Closer is called periapsis, the near point. Farther is apoapsis, the far point. You don't need to memorize the words. Just feel the meaning, near and far, like tides and distance. And with distance comes changing speed. When the planet is nearer to its star, gravity's curve is steeper. The planet moves faster, like a marble rolling through the deeper part of a bowl. When it is farther away, the curve is gentler, and the planet moves more slowly. Fast near, slow far. This is not accident, it is conservation. A trade between speed and position that keeps the orbit stable. You rest with this rhythm, approach, quicken, recede, soften. A year is not always evenly paced. On some worlds, seasons would not arrive with equal-length quarters. One half of the orbit could pass swiftly, the other half leisurely. Time itself would feel uneven under such a sky. The measure of how stretched an orbit is has a name, eccentricity. But tonight you can think of eccentricity as personality in path shape. Low eccentricity means nearly circular, calm and consistent. High eccentricity means elongated, dramatic and varied. Earth's orbit has low eccentricity. It is close to circular, which helps keep your climate relatively stable across each year. But many exoplanets, worlds around other stars, have much higher eccentricities. Some travel in very stretched ellipses, diving close to their stars, then wandering far out again. Their years are long swings instead of gentle loops. You imagine standing on such a planet. Your star would grow large and bright in the sky during the near pass, then shrink and cool as you drift outward. Temperatures could change drastically over one orbit. Atmospheres might expand and contract. Winds might shift direction with distance alone. Climate becomes a function of geometry. Why are so many exoplanet orbits more eccentric than those in your solar system? You let the question float without urgency. The answer often lies in history. Orbits remember past encounters. A close gravitational interaction with another planet, or even a passing star long ago, can stretch a once-round path into a longer oval. Space keeps records in curves. You return to the idea that motion is memory. The shape of a path tells you something about what happened before. A circular orbit suggests either a gentle formation or long-term smoothing. An eccentric orbit suggests disturbance, migration, or gravitational negotiation among neighbors. Nothing moves without context. There is also a quiet rule hidden inside all elliptical motion, a rule about equal areas and equal times. You can feel it without mathematics. Imagine drawing a line from the star to the planet as it orbits. Over equal time intervals, that line sweeps out equal areas of space, no matter where the planet is in its ellipse. Near the star, the line is short but swings quickly. Far from the star, the line is long but swings slowly. Fast close, slow far, perfectly balanced. Geometry and time agreeing with each other like matched breathing. You find comfort in that fairness. Even stretched paths obey steady principles. Variation does not mean chaos. Difference does not mean disorder. The ellipse is proof that stability can wear many shapes. You widen your view. Not all orbits belong to planets. Moons orbit planets. Asteroids orbit stars. Stars orbit galactic centers. The same path language repeats across scales. Ellipses appear again and again, nature's preferred compromise between freedom and restraint. Curves instead of corners. Returns instead of stops. You imagine drawing thousands of orbital paths with faint glowing ink. Around each star, loops overlap like threads in a nest. Some nearly round. Some long and narrow. Some tilted. Some resonant. A woven architecture of motion. No two systems look exactly alike. This diversity matters. When astronomers measure an exoplanet's orbit, its shape helps tell the story of that system's past. A very eccentric giant planet close to its star may have migrated inward after gravitational encounters. A set of nearly circular orbits packed tightly together suggests slow formation within a disk of gas and dust. Shape becomes biography. You let your breathing slow as you hold that thought. Paths are stories written without words. Distance and speed form sentences. Repetition forms paragraphs. Stability forms chapters measured in millions of years. And yet, even within one system, paths can evolve. Over long spans, gravitational tugs between planets can slowly change eccentricities. An orbit can grow more stretched, then less, like a heartbeat changing tempo. Stability is often dynamic, not frozen. Living balance, not rigid symmetry. You also notice something gentle and surprising. A circle is not more correct than an ellipse. A circle is simply a special ellipse, one where both foci merge at the center. The circle is not a different family. It is an extreme case of the same shape. Perfection, it turns out, is just one option inside variation. that idea settles softly. The universe does not separate the ideal from the real as sharply as humans sometimes do. The nearly circular and the highly stretched follow the same laws. They belong to the same grammar of motion. As you drift with these curved paths in mind, you begin to sense the distance from a star changes more than speed and temperature. It also changes how tightly gravity holds a planet's atmosphere, how radiation shapes its skies, how tides flex its interior. And you start to wonder about those worlds whose paths bring them extremely close to their stars, worlds where the ellipse nearly brushes the fire. You move now toward warmth, toward the inner edge of planetary systems, where distance grows small and motion grows swift. You imagine a star filling half the sky, bright and steady, pouring light like a waterfall of fire. Around it, closer than Mercury is to your sun, a planet circles in a tight, hurried path. 1 year there may last only a few days. Sunrise follows sunset with barely a pause. The orbit is so compact it could fit inside the space between your sun and its nearest planet. These are the worlds that hug their stars. They were among the first exoplanets astronomers discovered, and at first, they were deeply puzzling. Before their detection, you might have expected other solar systems to resemble your own small rocky planets near the star, large gas giants far away, cold and slow. That expectation felt natural because it was familiar. But the universe did not promise familiarity. The first widely confirmed exoplanets were hot Jupiters, gas giants as massive as Jupiter, yet orbiting closer to their stars than Mercury does to the Sun, giant worlds in tiny orbits. Heavy planets moving at tremendous speed. It was like finding a whale swimming in a bathtub. Expectation had to stretch. You picture one of these hot Jupiters circling its star every 3 days. Gravity holds it in a tight curve, and orbital speed keeps it from falling inward. The balance still works, the same gravity, the same motion, but the scale feels intense. Close distance means strong pull. Strong pull means high speed. The planet races along its path like a glowing ember caught in a whirl of air. Fast near, faster nearer still. Because it is so close, the star's gravity does more than guide the orbit. It also shapes the planet itself. Tidal forces, the difference in gravitational pull between the near side and far side, stretch the planet slightly. Over time, these tides often slow the planet's rotation until one side always faces the star. This is called tidal locking. You already know this pattern from the Moon. One face of the Moon always looks toward Earth because Earth's gravity gradually synchronized its spin. Many close-in exoplanets are likely locked the same way. One hemisphere lives in constant day, the other in endless night. A permanent sunrise line circles the globe between them, a ring of eternal twilight. You imagine standing there, where the star never climbs higher and never sets. Heat would pour from one direction only. Winds might stream from the day side to the night side in global currents. Clouds could form in strange, fixed patterns. Weather becomes geography. Closeness rewrites climate. Temperature on these worlds can reach extremes, often over 1,000 degrees Celsius on the star-facing side for the closest giants. Their upper atmospheres may puff outward from heating. Some even lose gas into space, forming thin comet-like tails trailing behind their orbit. A planet slowly evaporating under starlight. And yet, these worlds are easier to detect than distant ones. You understand why now. A close orbit means a short year. Short years produce frequent transits, many chances to catch that tiny dip in starlight. Close-in planets also pull more strongly on their stars, creating larger measurable wobbles. Their nearness makes their influence louder. They announce themselves more often. This is an important comfort. Discovery methods shape discovery lists. You find what your tools are most sensitive to. Early exoplanet surveys found hot Jupiters not because they are the most common planets, but because they are the easiest to detect. Like hearing drums before flutes, loud signals arrive first. As instruments improve, quieter worlds join the catalog. Still, a question lingers gently: how did giant planets get so close to their stars? Gas giants are thought to form far out, where icy materials are abundant and temperatures are low enough for thick atmospheres to gather. Close to a star, heat makes that difficult. So how does a Jupiter-sized planet end up in a 3-day orbit? The leading answer is migration. You picture a young planetary system, a newborn star surrounded by a wide disk of gas and dust. Planets form within this disk, gathering material as they circle. But the disk itself is not empty or still. It has density, pressure, and motion. A large forming planet interacts gravitationally with the disk, creating waves and wakes within it. Those wakes push back. Over time, this exchange of momentum can cause the planet's orbit to shift inward. Slowly, steadily, like a leaf spiraling toward a drain, the giant planet moves closer to its star. The disk acts like a soft conveyor, transporting worlds. Or sometimes migration happens later, through gravitational encounters between planets, close passes that fling one inward and another outward. Orbital energy gets redistributed. Paths get redrawn. The system reorganizes itself through interaction. Architecture through adjustment. You find this idea calming rather than chaotic. Movement after formation is not failure, it is evolution. Planetary systems are not frozen blueprints. They are living arrangements that settle over time. Some worlds travel far from their birthplaces. Distance is not destiny. Close-in planets also teach you about atmospheric survival. Smaller rocky worlds near stars may lose their atmospheres entirely if heating and stellar radiation are too strong. Gas escapes molecule by molecule. Magnetic fields, gravity strength, and stellar activity all matter. A planet's ability to hold air becomes a balance of temperature and mass. Retention is a quiet victory. You imagine two similar planets equally close to their stars, one massive enough to hold its gases, the other slowly stripped to bare rock. Same distance, different outcome. Details matter. Subtle differences shape futures. As you rest with these near-star worlds, fast, hot, reshaped by proximity, you feel your sense of what is normal gently expanding. Your solar system is one arrangement, not the arrangement. The cosmos allows many stable designs, including ones that once seemed unlikely. Variety is not error. It is expression. And as your thoughts drift along these tight glowing paths, you begin to wonder about another orbital surprise, not how close a planet orbits, but how strangely it might be tilted while it does. You begin this chapter by letting go of a quiet assumption. Until now, you may have pictured planetary systems like flat wheels, stars at the center, planets circling neatly in the same plane, like grooves on a record. This is a natural image. Your own solar system mostly follows this pattern. The planets travel in nearly the same orbital plane, aligned close to the Sun's equator, moving in the same direction. It feels orderly, layered, composed. But the wider universe does not always keep its wheels so straight. Some planetary orbits are steeply tilted compared to their star's rotation. Some even move in the opposite direction, orbiting backward relative to how their star spins. This is called a retrograde orbit, and at first encounter, it feels almost rebellious. But rebellion is only another name for history you have not yet heard. You imagine a young star forming from a rotating cloud of gas. The cloud spins gently as gravity pulls it inward. A disk forms thin, wide, turning in one shared direction. Planets grow from this disk, gathering material like snowballs rolling through mist. Naturally, their orbits line up with the disk's plane. Alignment is the starting condition. Harmony is the default at first. If nothing disturbed the system, the planets would continue circling in that same shared plane for billions of years. Flat, ordered, predictable. But space is not an isolated room. It is a neighborhood. And neighbors sometimes pass close. A passing star, even far away by everyday standards, can tug gravitationally on the outer parts of a young system. That distant pull can tilt the disk or disturb forming planets. Like a hand brushing the edge of a spinning plate, the orientation can shift. Alignment can be bent without being broken. There are gentler tilts too. Sometimes the star itself changes orientation slightly during formation if the infalling gas arrives unevenly. The disk keeps one direction, the star settles into another. Now the planets are not misaligned, the star is. Perspective decides the label. You feel how relativity enters even simple descriptions. Astronomers measure something called spin-orbit alignment, the angle between a star's rotation axis and a planet's orbital plane. For many exoplanets, especially close-in giants, this angle is surprisingly large. Some are nearly polar, orbiting over the star's poles rather than around its equator. A vertical path around a horizontal spin. How do you measure such a tilt across light years? Through another subtle signature in starlight. When a planet transits its star, it blocks different parts of the rotating stellar surface. One edge of the star rotates toward you, the other away. These edges have slightly different Doppler shifts, tiny color offsets in their light. As the planet crosses, it hides one shifted region, then another. This creates a delicate distortion in the star's spectral signal during transit, a small, temporary imbalance. By measuring that distortion, astronomers infer the angle of the planet's path across the star's face. From that, they calculate the orbital tilt relative to stellar rotation. Even alignment leaves fingerprints in light. You imagine watching this from afar, not seeing the tilt directly, but reading it from color changes smaller than a whisper. Again, discovery comes through influence, not image. Through pattern, not portrait. Many highly tilted planets are hot Jupiters, the close-orbiting giants you visited before. This connection is not accidental. The same gravitational interactions that can move a giant planet inward can also twist its orbit. Planet-planet scattering, distant companion stars, or long-term gravitational cycles can all pump up orbital tilt. Migration can include rotation. One important process is called the causative effect, a gentle but persistent gravitational conversation between a planet and a distant massive companion, such as another star. Over long timescales, this interaction can trade orbital tilt for orbital stretch. The planet's path grows more eccentric and more inclined, then tides near the star circularize the orbit but leave the tilt behind. The shape heals. The angle remembers. You like that phrase? It feels true beyond astronomy. Systems often smooth their distances before they smooth their orientations. Energy redistributes faster than direction. Tilt also affects climate and stability. A planet with a highly inclined orbit relative to a system's main plane may experience stronger gravitational perturbations from neighbors. Long-term stability becomes more delicate. Some tilted worlds may eventually be ejected or collide. Others settle into durable, if unusual, arrangements. Difference is not always temporary, but it is always meaningful. You broaden your view further. Orbits can tilt not just relative to the star, but relative to each other. In some systems, planets occupy multiple planes, like rings stacked at angles. Instead of a single flat disk, the system becomes a layered sculpture of motion. A mobile instead of a wheel. These architectures challenge early formation models and refine them. Scientists adjust their understanding, adding the roles of turbulence, stellar flybys, and multi-body dynamics. Theories grow more flexible as observations grow more diverse. Knowledge tilts to match reality. You find that reassuring science as adaptation, not insistence. There is also beauty in misalignment. A perfectly flat system is elegant, yes, but a tilted one is expressive. It shows that formation is not always quiet, that interaction leaves marks, that gravity writes not only circles and ellipses, but angles. Geometry becomes autobiography. You imagine drifting above such a system, watching planets cross the star at different slants, like brushstrokes of varying direction across a bright canvas. Each angle tells you something about encounters long past. Every orbit carries ancestry. Nothing arrives alone. Even in your own solar system, small tilts exist. Planetary orbits differ by a few degrees. Pluto's orbit is strongly inclined compared to the major planets. Many asteroids and comets travel on steep paths. The flatness you first learned is approximate, not absolute. Precision improves with closeness. Variety appears with distance. You let that idea settle, that simplifications are starting points, not final truths. First models are lullabies. Later models are symphonies. As your breathing slows, you sense a pattern across these chapters. Distance changes speed. Shape reveals history. Tilt records disturbance. Orbits are not just paths, they are archives. Motion is memory written continuously. And as more than one planet shares a system, each with its own path, tilt, and timing, you begin to wonder how their gravitational voices blend together when many worlds move at once. You drift now into a busier sky. Until this moment, you have mostly imagined one planet and one star, a quiet pair, moving in mutual agreement. A duet of gravity and motion. But many planetary systems are not duets. They are orchestras. Multiple worlds circle the same star, each following its own path, each pulling gently on the others. Gravity, here, becomes layered music. You picture a system with 5 or 6 planets packed closer to their star than Mercury is to your Sun. Their orbits are tight, their years short, their spacing careful. From afar, it might look crowded. From within, it feels choreographed. Each planet moves not only in response to the star, but also to its neighbors. Every orbit listens while it moves. When more than one planet is present, their gravitational tugs overlap. Most of the time these tugs are small, tiny adjustments to timing and position. A slight early arrival at one point in orbit. A slight delay at another. On short timescales, the paths remain steady. On long timescales, the interactions matter deeply. Small pulls accumulate like soft footsteps on a long road. You can think of this as conversational gravity. Each planet speaks continuously through its mass. Nearby planets hear that message as a changing slope in space. No single whisper dominates, but together they shape behavior. Stability becomes a group project. And sometimes, something beautiful appears from this shared influence, resonance. Orbital resonance is a rhythm relationship. It happens when orbital periods form simple ratios like 2:1, or 3:2, or 4:3. One planet completes exactly 2 orbits in the time another completes 1, or 3 while another completes 2. Their timing locks into a repeating pattern, like gears with matching teeth. You imagine 2 planets orbiting close together. The inner one circles quickly, the outer more slowly. If their periods fall into a simple ratio, their closest approaches happen at predictable points each cycle. The gravitational nudges repeat in the same places, reinforcing rather than randomizing. Repetition creates structure. This can increase stability, not reduce it, which might feel surprising. You might expect repeated tugs to cause chaos. But when the tugs arrive in rhythm, they become organized. Like pushing a swing at the right moment each time, energy transfers smoothly. Timing turns disturbance into support. Your own solar system carries resonances. Neptune and Pluto are in a 3:2 resonance. For every 3 Neptune orbits, Pluto completes 2. Their paths cross in projection, but the timing prevents collision. Resonance protects them through schedule. Order through rhythm. Some exoplanet systems show long chains of resonances, 3, 4, 5 planets linked in timing ratios like notes in a chord. Each orbit length relates to the next through near simple fractions. These systems likely formed in a gas disk where migration drew planets inward while resonance captured them into synchronized motion. Migration meets music and locks in step. You rest with that image, young planets drifting through a disk, moving slightly inward, and as they approach each other, gravity tests their timing. If the ratio is right, they click into resonance and continue together, like dancers matching stride. Not collision, coordination. Resonance also helps astronomers discover unseen planets. When one transiting planet shows timing variations, arriving a bit early, then late, then early again, it suggests a gravitational partner nearby. Even if that partner never crosses the star from your viewpoint, its rhythm is felt. You hear the hidden drummer through timing alone. These are called transit timing variations. The name is technical, but the feeling is simple. The clock is being nudged. A perfect orbit would transit exactly on schedule. A perturbed orbit keeps flexible time. the pattern of deviations maps the unseen mass. Again, motion reveals the invisible. But not all crowded systems are resonant. Some are simply tightly spaced and delicately balanced. Their stability depends on distance ratios, mass distribution, and long-term gravitational averaging. Astronomers simulate these systems across millions of virtual years to see whether they remain intact or drift toward instability. Prediction becomes a time telescope. In packed systems, there is a concept called Hill stability, a boundary that estimates whether two neighboring orbits are far enough apart to avoid disruptive close encounters. If spacing is too tight relative to mass, long-term crossing becomes likely. If spacing is generous enough, coexistence can last billions of years. Room is a kind of safety. You imagine shelves in a library. Books packed too tightly are hard to remove without disturbing others. Leave enough space, and each can slide out smoothly. Planetary spacing works the same way. Separation reduces conflict. Crowded does not mean chaotic, but it demands balance. There are also systems where a giant outer planet shepherds inner smaller ones, shaping their eccentricities and inclinations through slow gravitational cycles. Leadership, in gravity, comes from mass and distance. A far heavyweight can guide inner lightweights across ages. Influence does not require proximity, only persistence. You feel the scale of patience again. These interactions unfold over thousands, millions, sometimes billions of orbits. No hurry. No drama. Just cumulative effect. Like erosion, but in timing instead of stone. And sometimes, despite all balance, instability arrives. A resonance can be broken by migration or mass change. A close encounter can scatter a planet inward or outward. A chain can snap. When that happens, systems reorganize. Some planets collide. Some are ejected. The survivors settle into new spacing, quieter, wider, safer. After the crowd, a calmer room. You notice how often this theme returns. Present structure is not always original structure. What you observe now is the result of earlier negotiations. Planetary crowds may begin dense and resonant, then thin and spread. Or they may remain locked in rhythm for the lifetime of the star. Both endings are allowed. As you breathe slowly, you imagine listening to such a system not with ears, but with instruments, hearing layered periodic signals, each orbit a tone, each resonance a harmony. A gravity symphony written in years instead of seconds. Many voices, one center. And as you drift with that music of many pulls and shared timing, another possibility appears at the quiet edge of thought. What if a planet loses the orchestra entirely and travels on alone through the dark? You move now beyond the crowded systems, beyond the tilted paths and resonant chains, into a quieter possibility, a path with no center at all. Until now, every orbit you have imagined curves around something. A planet around a star. A moon around a planet. Motion paired with belonging. Gravity acting like a thread that always ties motion into a loop. But not every world remains tied. Some planets travel alone through interstellar space. No sunrise. No yearly return. No star fixed in their sky. They move on long, open trajectories through the galaxy, guided only by the combined gravity of distant stars and the galaxy itself. These are called rogue planets, though the word rogue sounds more mischievous than their story truly is. They are not rebels. They are released. You imagine a young planetary system still settling into balance. Multiple large planets form within the disk, each gathering mass, each pulling on the others. Their early orbits may be close, their spacing uncertain. Over time, repeated gravitational encounters occur near passes that exchange energy and momentum. Most encounters adjust paths gently. Some do not. If one planet passes another at the wrong distance and angle, the energy trade can be dramatic. One world may be pushed inward toward the star. Another may be thrown outward. If the outward push exceeds the star's gravitational hold at that distance, the orbit opens instead of closes. A loop becomes a line. Escape velocity is not only for rockets. It is a property of gravity and speed together. Every gravitational system has a speed threshold. Move faster than that at a given distance, and you do not return. You continue outward forever, slowing but never turning back. A planet can cross the threshold through gravitational slingshot. You picture it like this: two skaters glide close and push off each other. One loses speed and drifts inward. The other gains speed and glides outward faster than before. In planetary encounters, gravity provides the push. No contact needed, only curvature and timing. One falls closer. One flies free. This process is called gravitational scattering, and computer simulations show it is common in the early lives of planetary systems. Many systems likely eject one or more planets before reaching long-term stability. Your own solar system may have lost members long ago, early worlds flung into the dark before Earth finished forming. Absence can be part of structure. You let that idea feel spacious rather than sad. Ejection is not destruction. The planet survives. It simply changes context. From bound companion to galactic traveler. From year-based time to starless time. What is a year without a star? The question itself becomes gentle and strange. A rogue planet still moves, it simply orbits the galaxy directly instead of a nearby sun. The galactic orbit takes hundreds of millions of years. Seasons lose meaning. Day and night, as you know them, do not exist unless the planet rotates relative to distant starlight. Darkness becomes the default sky. You might wonder how such a world could ever be detected. Without a star, it emits almost no visible light. It reflects nothing bright enough to see across interstellar distances. Yet even rogues can be found, again through influence rather than image. One detection method uses gravitational microlensing. You imagine a distant background star and, between you and that star, a rogue planet drifting silently across the line of sight. The planet's gravity bends space slightly, which bends the path of the background starlight. For a short time, the distant star appears brighter, magnified by the gravitational lens effect. A brief brightening marks a dark traveler. The event may last hours or days, then fade forever as alignment ends. No repeat. No orbit to confirm. Just a single flare of borrowed light. From the shape and duration of that flare, astronomers estimate the lensing object's mass. Some of these events reveal planet mass lenses with no visible host star. A presence revealed by curvature alone. Surveys suggest rogue planets may be numerous, perhaps as common as stars, possibly more. The uncertainty is large, but the implication is soft and vast. The galaxy may be filled with unlit worlds, drifting between suns like embers gone dark. Loneliness, multiplied, becomes population. You consider whether such a planet could hold heat. Without starlight, its surface would cool over time, radiating energy into space. Temperatures would drop far below freezing. Atmospheres might condense and fall as global snow. Oceans, if present, would freeze from the top down. But not all warmth comes from stars. Inside a planet, radioactive elements decay and release heat. The core remains warm for billions of years. On Earth, this internal heat drives volcanism and helps power plate tectonics. On a rogue planet, internal heat might sustain a subsurface ocean beneath thick ice, especially if the planet is large and insulated by a dense atmosphere of hydrogen. Hidden seas under frozen skies. You imagine life not needing sunlight, only chemistry and stability, ecosystems like those near deep ocean vents on Earth, where energy comes from rock and heat instead of light. It is not proven that rogue planets host life, but physics does not forbid warmth below. Darkness does not always mean dead. There is also a quieter path to becoming rogue. Not all wandering planets are ejected violently. Some may form alone from collapsing gas clouds too small to ignite as stars. These are sometimes called sub-brown dwarfs, objects with planet-like masses born directly, not assembled in disks. Formation without family. Classification becomes fuzzy here. Is a planet defined by mass, by origin, by orbit? Science holds multiple definitions, each useful in context. You feel no need to resolve it tonight. Categories are tools, not walls. Nature is continuous even when language is discrete. You return to motion. A rogue planet still follows gravity, just on a larger stage. It curves through the galaxy's gravitational field, rising and falling through spiral arms over immense timescales. It is not lost. It is differently bound. Belonging can exist at many scales. If you stood on such a world wrapped in insulation, warmed by internal heat, the night sky would be astonishingly clear. No nearby star to flood the view. Only distant suns, sharp and countless. The Milky Way would arch overhead like frostlit smoke. A sky of pure distance. You rest with that image, a lone world, a bright galaxy above it, motion continuing without a local center. Orbit is no longer a loop but a journey. Still lawful. Still guided. Still part of the greater dance. And as you drift with these solitary travelers between the stars, another question begins to glow softly. When many forces act together across time, when small pulls accumulate and paths shift, where is the boundary between stable motion and beautiful chaos? You arrive now at the delicate edge, a place where order flirts with disorder, where paths that seem eternal can suddenly diverge. Here, the universe whispers that stability is never absolute, only prolonged. Time stretches long enough for patterns to endure, yet short enough for surprises to appear. Even in the calmest planetary systems, nothing is frozen. Gravity is patient but relentless. Every tug, every pull, even the gentlest, accumulates over countless orbits. The planets speak to each other continuously. Most of their conversation is subtle, a millimeter's difference in position, A second shift in timing, but repeated over thousands, millions, billions of orbits, these whispers can become transformation. You picture two neighboring planets circling a distant star. Their paths seem steady when you first watch. A transit occurs precisely on schedule. The radial velocity method shows predictable wobble. The system feels harmonious, almost eternal. But tiny differences exist, a fraction of a percent in speed, a slight tilt, a minor eccentricity. These differences act like seeds. They are small, almost imperceptible, yet capable of enormous growth under the right conditions. This is the essence of orbital chaos. Not all chaos is destruction. Not all unpredictability is random. Chaos is a sensitivity to initial conditions. Minute differences can eventually amplify into divergent futures. One planet's early perturbation might subtly alter another's orbit over centuries, then millennia. In time, a small nudge may decide whether two worlds remain comfortably apart or approach dangerously close. You let yourself feel the rhythm of this uncertainty. Time stretches, and the system is fluid. Stability is measured not as perfection, but as endurance. A planet may orbit for billions of years in apparent calm, only to find that accumulated gravitational influences will one day pull it into a collision course or eject it entirely. Predictability is a matter of scale, of patience, of perspective. Some systems exist in a delicate balance called the edge of chaos. Here, planets neither collide immediately nor settle into perfect harmony. Instead, they inhabit a region of slow evolution, where orbits shift gradually, resonances grow or break, and inclinations change over millennia. This edge is a living boundary between permanence and transformation, between predictability and surprise. You can imagine a cosmic weather map, not of wind or rain, but of orbits. Regions of stability glow softly, like calm seas. Areas of chaos shimmer with uncertainty, like storm clouds gathering over distance. Planetary motion moves through this landscape, sometimes anchored, sometimes wandering. Long-term simulations reveal which orbits are safe, which are precarious, and which may tip suddenly into dramatic change. Resonances, you recall from crowded systems, can stabilize planets. Yet, even resonances can be fragile. If a neighboring planet migrates or a distant companion star exerts influence, resonance can be broken. The planets may adjust, settle into a new rhythm, or face disruption. Stability is a negotiation, not a decree. You picture multiple planets in a compact system. Each orbit subtly influences the others, nudging, tugging, altering timing. The smallest deviations, accumulated over thousands of orbits, can create divergent outcomes, paths that start close together yet end far apart. Predicting motion far into the future becomes a matter of probability rather than certainty. Even a system that appears orderly now may hide future turbulence. This is the mathematical beauty of chaos. Equations describing these systems do not fail, they reveal complexity. Tiny changes in input produce branching futures. Some branches return to calm stability. Others diverge into dramatic instability. You feel the elegance of these branching possibilities. Each outcome is lawful, not random. Even chaos follows rules intricate, beautiful, and precise. You also sense the universality of these principles. Chaos is not limited to planetary motion. It emerges wherever systems are sensitive to initial conditions, in weather, in fluid dynamics, in the orbits of electrons in complex molecules. But here, in the quiet of space, you witness it on the grandest scale, whole worlds dancing on the edge of predictability, suspended between stability and upheaval. Stability itself is layered. Some systems are robust against small perturbations, nudges fade without consequence. Others are delicate. A minor encounter with another planet or passing star can cascade into large rearrangements. These contrasts teach patience. You learn that apparent calm does not guarantee permanence. Order is sustained by continuous negotiation, by the quiet reinforcement of gravitational rules, and by the absence of disruptive surprises. And yet, even in chaos, there is rhythm. You notice patterns emerging from the complexity. Orbits oscillate, inclinations swing, eccentricities vary in predictable cycles. These patterns allow astronomers to understand long-term behavior, to estimate survival probabilities, to explore the architecture of systems far beyond what human eyes can see. Even in unpredictability, there is structure. You imagine yourself floating among these planets, watching them for millions of years in imagination alone. One world drifts ever so slightly closer to its neighbor. Another moves outward. Resonances form and dissolve. Distances oscillate. Some paths are stable, some edge toward disruption, some cross into new, uncharted trajectories. You feel the tension without fear, the unfolding drama without urgency. Time stretches in a gentle wave. And yet, even on the edge of chaos, the universe does not discard order entirely. Systems may reorganize after disruption. Planets may settle into new stable orbits. Rogue worlds, once ejected, continue their lonely journeys along smooth, lawful paths dictated by the galaxy's gravity. Chaos is part of a larger rhythm and interplay between flexibility and persistence. You reflect on the beauty of this balance. Motion is not arbitrary. Even when unpredictability arises, it follows deep rules. Gravity, inertia, resonance, and energy constraints work together. What appears chaotic on a human timescale may be predictable across larger cosmic scales. Stability and chaos are not opposites but part of a continuum, a spectrum of motion and possibility. You breathe slowly, absorbing the interplay of certainty and surprise. You feel the universe's patience, its endless rehearsal of orbits, its careful dance between lasting order and transformative perturbation. Each orbit you have observed, each tilt, each eccentricity, each crowded system, contributes to this tapestry, a tapestry woven with threads of both harmony and disruption. And as you begin to drift with these thoughts, you sense a quiet question forming, gentle and reflective. If even chaos follows rules, if instability is lawful, then what can the patterns of strange, unpredictable orbits teach us about the meaning of our own home, the delicate balance that keeps Earth spinning safely through the galaxy? You drift now back toward familiar light, toward your sun, toward the planet that cradles you. The journey through distant worlds, tilted paths, resonances, and wandering rogues begins to fold inward, returning knowledge as gentle awareness. You see your own solar system not as ordinary, but as remarkable, a precise choreography that has endured for billions of years. You watch Earth tracing its nearly circular orbit, a calm loop close to the plane of the Sun's equator. The tilt is gentle, the eccentricity slight, the rhythm steady. Seasons change predictably. The sun rises and sets. Oceans flow. Winds circulate. Life thrives. You realize how delicate the balance is, how much depends on the precise combination of distance, tilt, and timing. After observing hot Jupiters hugging stars, rogue planets drifting through darkness, eccentric giants swinging in elongated ellipses, and tilted worlds tracing unusual paths, your own orbit appears both secure and improbable. It is neither extreme nor exceptional in mass or composition, yet it is fortuitously placed far enough from Jupiter's strong gravity to avoid destabilization, close enough to the Sun to maintain liquid water, and moving in a plane that avoids catastrophic perturbations. You feel gratitude, not as emotion alone, but as awareness of the rarity of circumstances. The vast galaxy contains planets that endure extreme heat or endless night, worlds flung from their birth systems, worlds locked in chaotic oscillation. Compared to these, your orbit is gentle, steady, hospitable. Stability is not guaranteed, it is a gift of cosmic architecture. Even the other planets in your solar system play a role in this harmony. Jupiter's presence acts as a guardian, its gravity capturing or deflecting many comets and asteroids that might otherwise threaten the inner planets. Saturn's resonance structures maintain order in the asteroid belt. The orbits of Venus, Mars, and Mercury, while individually modest, together weave a tapestry that reinforces long-term stability. You think of the lessons learned from distant systems. Tilted orbits, eccentric giants, packed chains, rogue wanderers, each demonstrates that planetary motion is fluid, adaptable, and sensitive. The calm predictability of your world becomes precious precisely because it is rare. Stability exists, not by necessity, but by circumstance. The Earth's path is a balance achieved among countless possibilities, a quiet miracle written in gravitational notes over eons. Your mind drifts over the sky at night. You imagine exoplanets passing in their orbits, some visible only as subtle dips in starlight, others forever hidden in dark interstellar space. Each has a story of migration, scattering, or resonance. Each orbit records history. In comparison, your sky, familiar, steady, predictable, glows with the privilege of survival and timing. You feel a gentle reverence for ordinary stability, understanding that it is extraordinary in context. You also see reflection in comparison. Strange orbits illuminate your own system's virtues. The extremes of proximity, tilt, and eccentricity are mirrors that show what could go differently, what balance requires, and how fragile order can be across cosmic time. The knowledge deepens appreciation. What is normal here would be exceptional elsewhere. What seems mundane is in fact carefully arranged. Earth's orbit is a quiet lesson in moderation. It is not the fastest, not the most extreme, not the most eccentric or tilted. It does not race close to the Sun like a hot Jupiter, nor wander as a rogue planet. Instead, it is a carefully measured journey, just stable enough to support climate, water, seasons, and life. Its grace lies in precision, in gentle eccentricity, in predictable repetition. You reflect on the interconnections. Every orbit, from the most extreme to the most placid, follows the same laws of gravity, the same rules of motion. Variation is allowed, chaos is lawful, stability is provisional. Each system is a realization of these principles, sculpted by initial conditions, interactions, and time. Some remain steady, some evolve, some drift alone. Observing them all illuminates the extraordinary balance that sustains your home. Even the sun's own motion within the galaxy reminds you that stability is local, not absolute. The solar system drifts along a path around the Milky Way's center, moving through spiral arms, encountering subtle tidal forces and occasional stellar neighbors. The Earth's orbit is a nested path within larger orbits, an order within layers of motion, each influencing the other subtly, each subject to the long dance of time. You picture nights stretching back through the ages. Generations of planets have migrated, collided, been ejected. Rogue planets traverse space silently. Giant worlds swing close to their stars and return. Tilted and eccentric paths trace the memory of gravitational interactions. Stability is provisional, survival is conditional, yet your orbit continues. You are part of this narrative, a participant in a vast, layered story. And you realize the lessons are not only scientific, but poetic. Motion is memory. Orbit is biography. Paths reveal history, interactions, and the passage of time. Order emerges from negotiation. Chaos and stability coexist. Every orbit, whether calm or extreme, tells a story of circumstance, energy, and connection. Looking up, you see the night sky alive with these silent narratives. Every distant star may host worlds of extreme heat, cold, tilt, or eccentricity. Some stars harbor quiet chains of resonant planets. Some planets wander alone, unanchored yet lawful. Each story parallels and contrasts with your own. The Earth's orbit, steady and life-sustaining, is both ordinary and remarkable, a refuge in a galaxy of extremes. You feel the rhythm of the cosmos. Motion, distance, tilt, resonance, ejection all form a gentle pulse, a quiet music of celestial balance. This music has played for billions of years and will continue, unseen and unfelt by most. Yet through observation, imagination, and understanding, you can trace its melody, recognize its patterns, and feel your own place within it. And as you rest beneath the night sky, reflecting on the journeys of distant worlds, the lessons of rogue wanderers, the discipline of resonance, and the edge of chaos, you allow a gentle awareness to settle. Stability is a gift, rarity is a guide, and the ordinary orbit beneath your feet is extraordinary in context. The sky above you no longer feels empty or static. It hums with stories of motion, with histories written in curves and angles, with lessons in balance and chance. And as your breathing slows and your eyelids grow heavy, you carry this understanding softly. Every orbit, every path, no matter how strange or familiar, is a story, and your own world is a story that continues, quietly perfect, in the gentle rhythm of the cosmos. And somewhere beyond sight, other planets circle, tilt, drift, and wander, a universe alive with motion, waiting for your imagination to return again.